shall we begin? I have sound too. Hello everybody, I am Manu of Brisbane, and thanks. So I've been working in the video games industry for about 10 years now. I'm usually an engine or a sort of a general tech programmer, and last year we did some practical experiments with using D in a video game, and I'm here to discuss our experience. This is a good question. Let's find out. I did notice, however, while writing this presentation, that the video game part of it's kind of incidental. It's really just sort of, I'm going to talk mostly about the framework. That was the most interesting part that I could sort of come up with related to D. And it's really just about dynamic interaction with C++ in general. So maybe it's got use elsewhere too. So the story goes. It all started one day with a meeting among the tech programmers. We had congregated to discuss the possibility of a scripting language. The problem was C++, compile times, link times, and then program reload, restart times is really slow and really painful. Wastes an awful lot of our time every day. So we concluded that us programmers would like to have something of a scripting language for rapid iteration, let's say. We had no real preconceptions coming into this. We were sort of considering some high-level languages like Lua and GameMonkey, and these are nice lightweight libraries that are already popular in video games. Also on the table there was the sort of the standard JITs, Mono and LLVM, with the expectation that we'd use C# or something, which everyone is familiar with. Sorry. But one of my colleagues, who previously worked at Splash Damage with their idTech engine, threw a kind of left field idea on the table. Turns out that idTech uses a system where they build C code, normal C code, into a DLL, and then they built a framework around it, which dynamically loads and can unload and reload these DLLs on demand based on changes in real time. Does anyone recognize that guy? He always says that. So we're considering the trade-offs here. Lua is nice and lightweight. It's a simple-ish language. Everyone likes it. But unlike most commercial, like video game studios, which are sort of implementing scripting for primarily their designers to work with, this one was really a language for our programmers to use. And we liked the idea of being able to use sort of more intensive routines in this context. So, I don't know, Lua was not so appealing to us. So then we considered the C# thing. Good performance, nice modern language, but then we started looking at the libraries themselves, and it turns out Mono and LLVM are both huge libraries, and integrating it with our engine is a pretty big job as well. And from that, we just sort of kept on drifting back towards this idea of using C inside a DLL. It's fast and it's pretty lightweight, really, but we're stuck with C, which sucks, but we're accustomed to it, so maybe it's not so bad. But then something happened. As a D enthusiast, I made a joke that we should use D in place of C++. So D's fast, and it's nice and modern. That's cool. It's also pretty lightweight, you know, other than we've got one additional standard library that we need to link now. Otherwise, it's sort of the same as what we were looking at. There's also another couple of key benefits. One is that it compiles lightning fast, which is the rapid thing we're going for. And D's powerful template system may really help us with the bindings. And I don't know how many of you have tried to bind a dynamic language like Lua up to your code, but it's a big job. It's just messy and cumbersome. There was a good opportunity to automate that in D, I think. It turns out that my colleague, who suggested this C in a DLL approach to begin with, had a passing interest in D and was curious himself. So we started to talk seriously about it. So we took this back to the team. And to my total surprise, they were basically unanimously interested. Now, these are Finns, mind you. Finns are extremely conservative people, so I was basically gobsmacked. One question did continuously come up, however. This is it ready? We couldn't really point at any big projects and say, look, there it is. It was a success. Hooray. So, it's a fair question, I think. Our strategy here was to try and hedge our bets. We'd build this framework such that it was originally meant to be based around C, which is another native language compiled in a DLL. We can build a framework that works with either language. If it turns out that D goes south for whatever reason, we can insert C or C++ straight back into the same context, and we haven't really lost too much. Like so. So thus it begins. So we had a few requirements. Let's talk about the actual framework. I'm going to mostly talk about the framework itself, actually. I think the other stuff's not so interesting. And the framework's implementation showed a few problems and issues that I'd sort of like to generate some discussions about. So we're a Windows/Visual Studio studio. Turns out that most of the D community is not into Windows. But there was this wonderful Visual D plugin, thanks to this man over here. Mr. Rainer Schutz. And we may not have even proceeded if it weren't for the existence of this plugin. It just wouldn't have been a consideration. The IDE is critical. This was a little stumbling block. We have to target Win64. We also require symbolic debug information. Bummer. So what are our options? We took a look at LDC. I think at the time I first looked at LDC, it was still on D1, which must have been early last year. And even today, it still doesn't properly support Windows 64 exceptions or the debug info that we can use. So sadly, it's off the table, but it's a nice compiler. I hope it gets there. GDC, however, had a working Win64 toolchain. There were 2 enthusiastic developers. It was good for a prototype. And prototype we did. Until we started running into bugs. We started hitting these bugs, and then we found, well, firstly, I'd logged the bugs in the bug tracker. And it was tricky for us to predict which bugs would be fixed and when. We talked to Walter and Andre about this, and they lent their influence behind the bugs that we were interested in, and they got prioritized. So a patch appears, and we found then that there was a roughly sort of a 2-week turnaround between a patch to DMD and a new Win64 toolchain. At the end of this 2-week cycle, we'd find another bug the very next day and repeat. It just wasn't sustainable, sadly. We really need DMD. We need the frontline compiler. We need to be able to depend on, if there's a critical bug that comes up during some sort of a crunch time, there's guys on our side that can help us sort it out quick and get us a build. So I chatted with Walter and Andre, gave them our story. They thought it sounded great. I think they were enthusiastic. and agreed on a goalpost for DMD Win64. I'm sure Walter never said that out loud. A couple months later, we've got a Win64 compiler, and we're happy. We're back on track. So, what do we do with it? The goals of our framework. Obviously, rapid iteration is our primary goal here. We want to be able to edit high-level code, tweak it effectively, and see the results of those changes in-game running as fast as possible. We also require dynamic linkage so that we can change these things out while the game is hot. We need full interaction with the engine to make useful code in this plugin context. We need to be able to offer new functionality to the engine that it can make use of. and we need to retain the state of live objects in the world across an update cycle. That's interesting, we'll get back to that. So, rapid iteration. Turns out that in our company, we have a solution for rapid iteration for many art assets already. On the dev PCs, there is this file system monitor service. Everyone's running this service. It keeps an eye on the game data directory at all times. When the game is running, it creates a connection to this service and they talk. So when an artist, let's say, comes along and saves a texture, Mr. File System Monitor here notices that the texture has been updated and informs the game, which can then reload it instantly, and it appears on screen. And this is great. We should leverage this system. So for D, how exactly do we do this? So firstly, we treat the D code like it's data to fit in with our environment. When a programmer comes along and saves his source files, Mr. Service notices again, rebuilds the module, and informs the game to reload it. Now, there's a magic step in there, this rebuild step, which is a little bit trickier for code than it is for a texture. For a texture, for instance, it's pretty simple, or most asset types. It's basically a one-to-one mapping between this source asset, like a PSD or something, and it munges it into some platform-specific texture. It's an easy conversion, but for code, there's a whole bunch of code. And it all gets compiled and all linked together in a completely arbitrary manner. And there's nothing in the file names to give us any hints about this. So how do we approach this? Firstly, we create a directory called plugins. In this directory, we nominate these to be effectively entry points to modules, to what we call plugins that will be loaded by the game. Each of these entry points will produce a DLL of exactly the same name. And it compiles in a two-pass process. The entry point module gets pushed through the compiler, but it produces no output, except for this dependency list. So once it resolves the full import hierarchy, we can have it produce a full dependency list at the other end, which we can then take along with the original module and push through the compiler altogether, which is able to produce a binary. And then as a nice little bonus, we split off another thread and do it twice. We now have a debug binary and a release binary, which we can switch between at runtime to test performance and or place breakpoints and debug. So that's good. Turns out that this process is lightning fast, thanks to DMD. This is the kind of rapid I'm talking about. 2 seconds, for a smallish plugin, I'm seeing about 2 to 3 seconds turnaround for this whole two-pass process. Really happy with that.
As opposed to?
Oh, okay. As opposed to, sorry, I need some water. As opposed to GCC, I think previously was taking between sort of 20 and 30 seconds with the full link times. Most of it's link time, I think, and GCC's optimizer is not amazingly fast. Cool, so now we've got our plugin DLLs. We need to load them somehow. We basically have this plugin manager in our engine, which on boot scans for any plugins available and just loads them up. When it receives an update signal from our monitor service, it runs this process where it first saves the state of all live instances of objects created by these plugins. Then it unloads the DLL, reloads the rebuilt DLL, and it recreates the object's instances from the saved state. And I'll get back to how that works in a little bit. I won't talk about the implementation, it's not particularly interesting, and yes. So interaction with the engine. This is the biggest, trickiest, hairiest bit. So we have our system. Turns out it's not so simple. D needs access to almost everything about C++. Structs, static functions, and classes. And we'll look at each of these. So firstly, the structs. This is fairly straightforward. We just mirror the definition in a D module, and it works. Sadly, I don't have any way to assert that the C++ structure and the D structure remain in sync. I'd like to address this somehow. I don't know of a C++ template solution to do this. Maybe there is one. I wouldn't consider myself a C++ template genius, but functions are a little more interesting. So D supports the C++ calling ABI and calling conventions. That's good. So in C++, we just need simply a registry of functions that we want to export to for the plugins to use. And on the D side, we'll generate modules with a whole bunch of stubs that get linked back to the engine exports on module load. Not so hard. So here's a nice little C++ function that we want to export. We've got this funky little macro here, export function, which just adds it to the export table. No problem. And in D, we can declare a big extern C++ function pointer. And we have this funky little register mix-in register module. And that implements a whole bunch of magic which performs the dynamic hookup on module load. It looks kind of like this. We have a module constructor. It registers a function which is called on module load that finds in the import table rather all of the eligible function pointers that so it does a scan, right, using CTFE and all that stuff. It does a scan of the module. Any eligible function pointers that it finds, it can find them in the import table by name, hook them up to their function pointer, and then they're all live. It's okay. I'd like to think we can do better than this. This function pointer syntax is pretty ugly. If you go looking at this module, you can barely read it. But most importantly, this function pointer syntax doesn't support overloads, which are quite critical. So, if you lobby for a feature, or perhaps a bug to be fixed, where you can prototype a function and declare the function in the same module, which wasn't previously possible, we can do something like this. We can prototype the function, and then we can enhance our little register module mix-in here to find the prototype and generate a little stub along with the function pointer, which calls through the function pointer, and everything else remains the same. It hooks it all up magically. That's nice. We can perform overloads this way. But there's a few other details in the overloads. So in C++ here, we want to register an overload. So our export function macro here has a little problem. We need to pass along the types for disambiguation. A nice little bonus of having these types now is that using C's awful macro stringification, we can generate a nice little signature string like this, which we couldn't do with C templates for the structure case before. And we can pass this through to D. Now on the D side, we have our overloads prototyped up here. And our find function call here can quite easily, using a little D template, from the function signature produce a string that looks the same. That way it can hook up the correct versions to the function pointers. And that's nice. And of course, we need to mangle the function pointer names now. So this is working. We've got overloads happening. We found this happen. Hello? Yep. This is obviously a common C++ pattern for passing an array. You pass a pointer to an array and a explicit size argument. In D, this isn't really nice. We'd prefer to avoid this. It's much nicer to have a nice little wrapper like this, which receives a dynamic array and can split it and pass the pointer in length directly. We'll make the function pointer private. Now the problem came up where our little register module macro couldn't distinguish between the actual local function or the generated stub. So if you lobby some more for some cool features, you can do this. Now we have an import attribute. Hooray! So we can tag our prototypes with import and enhance register module again to recognize import directly. That's awesome. This is starting to feel nice and neat and tidy now. So that's functions basically taken care of. I think that's solid. Classes get a bit more tricky again. D doesn't interact with C++ classes very well at all. You can't extern to C++ static methods. There's no syntax for it. Virtuals are a little bit tricky. The static method situation, so exporting these from C was basically the same thing. We just export the function pointer via the same method. This exports a C++ member function pointer, not a delegate. On the D side, we implement the class like this. We use a struct to express the C class for hopefully obvious reasons. We can declare the method, prototype again with our little import, but now we need a new mix-in here, register class inside the class scope so that it can produce the stub in the correct location. Now there's an extra bonus here when it's producing the stub for the method, because we can't interface a C++ member function pointer directly. We kind of had to abuse our knowledge of the C++ ABI. This is lovely, I know. So we declare a function pointer, and we know that the first argument is, of course, this pointer, so we explicitly insert that in place, and in our little stub, we pass through the address of this. Sadly, this is not portable. But it worked for us for the time being. I'd like to think there's room for improvement there. And virtuals. So here we have a C++ class with a virtual in it. We don't need to do anything. That's great. On the D side, we leverage this, the interface concept. So D can communicate with C++ virtual tables via this extern C++ interface concept. It will basically treat the interface just like a C++ virtual table. So we, on the D side, now have to create an extern C++ interface that matches the virtual table from our C++ class. Sadly, this is sort of separate from our class definition, but it's okay. Now our fake class here gets a bit creative as well. So we have our struct engine class here. We need to make a struct able to interact with a virtual table. So what I did was created this little property vtable which casts ampersand this into our engine class interface. And then using alias this, we can make these virtual methods accessible from our struct. Not too pretty. Maybe I can wrap that up in the register class mix-in, but I kind of want to get rid of that mix-in in the future. So that's good. Actually, that's classes. That's everything, actually. We can now communicate with C++ pretty completely. I can't really think of anything that... Oh, templates are obviously a problem, but they just need to be mirrored. So now the game needs to make use of these plugins now. Plugins are capable of producing useful code. We effectively want the same set of features in reverse. But since there is no existing code in the plugin infrastructure, we can make a whole bunch of restrictions to simplify the interaction. So what do we actually want? I think first we want to be able to access D static functions for just very simple sort of RPC type function calls. And classes are a bit tricky. We want to be able to use D classes to express new entities that we can place in our game world, but trying to interface a D class on the C++ side directly, trying to express that class structure on the C++ side would be fiddly, so we'll treat class pointers in C++ as opaque, and we'll interface with them via D's interfaces explicitly, or exclusively, I should say. Sounds good? So firstly, let's look at the static functions. It looks like this. We have a D function. It needs to be extern C++. We tag it with export. Register module does the rest. In C++, we have our plugin manager here. We can simply find a function by name, and it returns this funny little template which effectively implements a smart pointer to the function. This is so that when the plugin gets pulled out from beneath it, it can fix up the pointers later. And if it gets a valid function, it can call it. It should always check that. If the plugin's not loaded or not present, then the code should try and handle that case. Yeah, I just said that. This is an interesting point, though. Going from C++ to D, because we have that nice little signature string that we managed to manufacture with the C macro, we can assert that the signatures remain in sync. Coming this way again, we have the same problem with C++ templates. I don't have a solution for making sure that the C++ code and the D code signatures remain in sync. I, again, don't really know what to do about that. We just have to hope. So a class in D might look something like this. We export an extern C++ interface. This is the interface that C++ will make use of. Our register module mixin gets some new tricks. So in the module constructor, it registers the interface by name. It also registers along with it a small little function which can perform a cast from object to an interface of that type. This is so C++ can cast its opaque D class pointers to something useful. And then the class, which we implement any number of interfaces that we're interested in, also export. It'll register it by name along with two little functions to create and destroy instances of the class. Very good. On the C++ side, we have to mirror the interface as a C class with a bunch of pure virtuals. That's straightforward enough. And we can create new instances of classes by name. We get our opaque D class pointer. This is, again, another one of those little smart pointer type things that will double indirect so that we can pull them out and recreate them. Then we can query for interfaces by name. If we happen to find the interface, we can use it, and later on, of course, we can delete the class. It's good, works. So we have everything we need, I think. We can create new entities that exist inside the game world, and they can do useful stuff. But what happens when the live class definition changes? Yes. So our final goal here is retaining the object state across one of these rebuild cycles. So let's say we've got a class that looks like this. We've got Mr. Dude here. He's got a position and health. And we decide that he wants velocity. So we've got a whole bunch of live existing objects, and we rebuild the code and pull it in underneath. Now the new code is incompatible with the old object instances. So we effectively use serialization to mitigate this problem. The approach here, plugin manager keeps a registry of all instances. Every time you create a class instance, it will put it in some registry, so we know about all of the life of all objects in the system. We enhance again our register module mixin, which is full of magic, to produce a serialization function for any class or struct that it happens to find in the module that it exists. So the reload process goes. All instances are serialized to text via the magically created serialize functions. Then we destroy all the instances, unload, reload the plugin, and recreate all our instances from text. New members obviously take on default values. It more or less works pretty well. But there's a couple of little edge cases. Obviously, if a variable changes meaning significantly, we can still see a crash. If you know, states of variables become invalid from one revision to another, we can see a crash. But programmers know how to avoid this. So you know, it's a nice, practical, workable solution, and it's doing business. So we have a system that's working well. A few rough edges. Every single module needs to have this magic mixin declared. I guess that's okay. Every class requires another one. I'm not so excited about that one. It'd be nice if attributes, for instance, could introduce code directly. What we have to do with these mixins is run some meta which scans the module for all things that are tagged. And it's these scans that are really annoying. If the presence of an attribute could some way introduce code, maybe that would help us a lot. Also, we could probably do all of the class stuff inside the outer register module mixin if it were possible to declare a class method outside of the class definition, but I don't know, just thoughts. And the other big problem here is we can't assert that structures or virtuals remain in sync in any way. Or that D functions returned to C++ remain in sync, but these are really deficiencies in C++. I'd love to hear ideas. There was one other issue too that I didn't put on this slide, and that's that really brutal explicit insertion of the this argument into the function pointer. It'd be nice to make that system portable. So we have a system. Hooray. What makes it worth all that effort? So it's working now. That was a decent bit of work to sort of fiddle around and get all the meta happening. What is it that the programmers appreciate about it? This may seem trivial, but it's not. Coders love ranges and for each, and slices are seriously awesome, and they just declutter your code. And that's sort of the point. You know, this is meant to be for iterating higher level code for us. Quick tweaks. It's nice if you can come into it at a glance, read it, and understand it. Attributes also have the same effect. For each, obviously, should not be underestimated. Two, I haven't talked about it here, but we invented an event-based programming model. Most game devs are familiar with C#, and by extension, its event-based programming model, which is pretty nice. It's very hard to emulate in C++. Proper delegates in D facilitate, a nice framework. Turns out, too, that C++'s fast delegate library is, in fact, perfectly compatible with D delegates, and I bet that's not an accident.
That's not an accident.
Thank you, sir. So another one that we're into is D finally does something about the SIMD problem. We've got standardized SIMD types now in D, and in the future with standard.SIMD, hopefully we can have a fully standardized portable SIMD interface. For the time being, if you've ever tried to do SIMD programming across platforms and on various C++ compilers, it's a real pain in the butt. And wrangling the optimizers is equally difficult. So that'll be really good. Another little bonus that we quite appreciate is this ability of OptDispatch to provide something that we all like from HLSL and GLSL, which is this ability to swizzle vectors. So an awful lot of our code is linear algebra. So here we have like the standard linear algebra cross-product function. It does this vector1.yzx times vector2.zyx. It sort of multiplies the other other elements by each other. Swizzling in this way is really nice, and the fact that D can express something like that with OptDispatch is really cool. There's been talk. Hello. Yeah. I'm curious to see where that goes. I think there's opportunity for sort of cool stuff there. Theoretically pure, I think, should offer us a whole bunch of wins in intensive maths code, but I'm yet to see that actually in practice. But I hope it gets there. And attributes, of course, are extremely awesome. They, again, really help to simplify code, and that's what we're all about, really. It's really helpful to see what class members do at a glance. And here's some ideas that we use. So we've got this save game attribute here, for instance. We can simply control the things that get put in the save game file. Bam, done. Hooray. This is a cool idea. We can tag something with profile, and we'll get a nice little on-screen real-time graph that charts that variable over time. We got this little tweakable guy here, so you can tag something with tweakable. Now the designers have this on-screen menu where they can go through a list of things that are registered as tweakables, and they can tweak the values at runtime and see exactly what they do, which is very handy for gameplay tuning. And this is one of my personal favorites. You can tag something with editor and then associate with it a nice name and some other little details. And our editor can load the plugin, ask it for all of the editor information, and just populate the editor with these new objects, just based on the code definition alone. So now we can place our class in the scene and automatically populate like a property grid with all of the stuff that you can edit, and the designers can go to town on it straight up. And of course, if you edit it and change it later, then you don't need to do editor updates and all that rubbish. That wastes a lot of time, actually. Like, there's a huge amount of work that goes into maintaining editor consistency with games. So that's cool. I'll finish up with some final thoughts. So the video games industry, at least the big games industry, there's a whole new emerging mobile thing which is exploding, but I've been stuck in big games forever. And we're still stuck with C++, and I don't see us ever getting away from it. We're on embedded hardware. We need to write native code. If we're not pushing the benchmark, the competition will. Native code is a requirement. It's also a high-risk industry, thoroughly allergic to change. You know, trying to suggest to a game dev studio, hey, you should try a new language, no, not even. But we're always pushing these aggressive schedules and working crunch and late nights, and C++ wastes just inordinate time and sanity. It's incredibly frustrating. It's like a daily talk point, probably more like an hourly talk point, you know, between programmers swearing about C++, what it's done to them today, and how much it's hurt. We are, in fact, an industry desperate for salvation from C++. And using this approach, at least, we can sort of test in a nice little isolated environment. If it proves successful, we can slowly wean ourselves towards it. Because it's actually a native systems language, I'd like to see, we can statically link it against the rest of our code. We can hopefully see it start to infiltrate the actual game engine and you know, slowly erode the C++ code dependence in the future. And may we all live happily ever after, indeed. So that's it. Go for it.
So you had an issue with like the imported. You had an issue with imported attributes in your code that were kind of have to add it to each class and each module. So maybe you could instead have a string import module and then instrument the string to add those attributes, and then you don't have to change, or this would all be automatically done.
A string import module.
So instead of import, you can do string import, and then you can instrument your code to add those.
Okay, I see what you mean. Yeah, that's an interesting idea.
Another question I had is, isn't a lot of stuff on your first third of the talk, could that be done with Swig? Because a lot of it is similar. It has like it uses runtime loading.
Yeah, it possibly could be done with Swig. In my experience with Swig, and we've used Swig a lot to bind other languages and C# in particular, it's not perfect. Swig kind of, it can do an okay job, but it can't do a really good job, and I'd rather take the time to do a really good job once, because these sort of like the big engine systems don't change very often. Most of the engine tech is pretty static. It's this high-level game code that we're iterating most frequently. So I'd personally rather hand tune this, like you see with those little wrappers and stuff. I'd rather take the time to generate the nice little wrappers to really deify the API, and not just use the C calls directly.
For keeping the stuff in sync, have you considered having the macro wrappers on one side or the template wrappers on the other generate the other one?
Yeah, I've thought about it. So which side would it be? It would be easier for the D side to generate the C++ side, I think, but that's not the way it goes. We've got an existing C++ code base. Now, I had also thought about doing it the other way. Like, I really wonder if can mixins actually, can CTFE access the file system?
Yes.
So I had a wild idea at one point about creating include, like a mixin include blah.h.
Well, there's no particular reason you couldn't write a full-blown C compiler at compile time.
Yeah, well, at the very least, some sort of a parser which might be able to parse the C header files and make available.
I know exactly how crazy
what
that is.
you'd lose again like that nice sort of fine tuning of the D API, but you could probably add that on top, I think. I'd like to experiment with that. I didn't actually know if it was all possible, and I certainly haven't had the time to try it, but it was on the list.
Yeah, but in answer to your question of who generates what, I think it'd just be whoever owns the original type generates the other one. So you may actually end up doing both.
Yeah.
So this is more of an observation, but I thought your use of attributes to denote things that can be tweakable by designers, it's such a key important thing for us all to think about as software engineers is the people who are good at making things bouncy and fun and easy to touch are often not the people in this room. Like, I can't draw like at all, and my handwriting is terrible. But I think making software that has the knobs that the artists can tweak and play with. There's a game I recently played called Rayman Origins, and it looks like hand-drawn Disney animation because all the programmers did was make a toolkit to let the designers design the way the characters move and bounce and run around, and it feels like a cartoon, which is nothing I've ever seen before.
Like,
so we can learn a lot from that.
This was, I saw that as a massive advantage. Those little sorts of details, whilst they might seem trivial, should in theory have a big effect on what we can offer to the designers. You know, just the depth that the designers would be able to.
Not just designers, but data scientists and other specialists who may not be programmers, but they want to reach in and tweak and twiddle with things. Like, that's a really good way to do that.
Yeah, it is. It really is.
Okay, 2 words, garbage collection.
Thank you. I was waiting for that one to come up. We weren't really ready to place our faith in the garbage collector at this point. It's in my experience, unreliable. I've seen it leak. We more or less banned it, and we avoided it at all costs. When I use the new operator before, we don't. I use malloc and in place. We explicitly manage our memory still, even inside the D context. We are using the garbage collector a tiny little bit every now and then when there's some local dynamic arrays and they're concatenated and things like that. The garbage collector might come up, but it should be very short-lived items. Nothing long-term ever is allocated by the garbage collector. We're just really conservative with it. Maybe with more time and experience, we'll gain more faith in it, but for the time being, we try to avoid it at all costs. And sadly, for the time being at least, that means almost entirely avoiding phobos. Even really, really benign phobos functions that have no business allocating memory, almost always allocate memory for, you know, I don't know why. It'd be really nice to benefit. In fact, it's something I've been interested in just doing at some time when I've got some dead time, is just going through and start trying to trim allocations out of phobos for kicks and profit.
So I got a question over here.
Yeah.
Have you documented all this so other people can use your C++ linkage stuff, or is it all proprietary?
It's proprietary, but I actually want to. There was a lot of learning experience in there. I'd actually quite like to have a second shot at this and make it open source. I think that would be valuable. And like I said, I don't think this system's exclusively for games. It's just really about dynamic binding to any code. Yo.
It's becoming a sort of a leitmotif here, this whole, you know, functions allocate memory, although it's surprising that they do. Well, so there's 2 things I wanted to talk about regarding this particular issue. Number 1 is std algorithm is one function away from doing no memory allocation.
Okay.
And I've had it's in Levenstein distance. It allocates the intermediate buffer for history. So once that's done, essentially a std algorithm is going to be, you know, stamped with, you know, does not allocate memory. It does allocate memory in a scoped manner sometimes when needed for temporary buffers. It does not take the initiative of allocating memory and kind of escaping it. So that's a good thing, I think. And the second is if this issue is becoming more endemic for D in performance-intensive code, you know, probably it would be a good thing to start discussing, like, you know, during mingling times about this whole @nodegc attribute, which is semi-magic, is recognized by the compiler. Like, this function does not allocate garbage collector memory, and we should essentially start to talk about what kind of benefits versus difficulties that approach entails.
Yeah, I have another thought too. An awful lot of these functions just don't need to allocate, but they do. People do it for convenience. People are always just slicing and concatenating and doing stuff for convenience all over the shop. It'd be nice if in Phobos people would take a little bit more care. This is the standard library. It will be used by everyone everywhere all the time. it it deserves a little bit of time to improve that at least as much as possible. Like, for instance, I found a function the other day, to upper in place. It receives a string and is meant to perform a to uppercase conversion on that string in place, and somehow that allocated memory. You know, go figure. Like, everything allocates.
Linux?
Sure, why not?
So nothing is particularly bound to Windows.
I don't really see why a shared library wouldn't work in place of a DLL. You can manually manage them too.
But would your code actually work with it?
I don't see why not, especially, okay, let's imagine it gets open source, then you can come along and add shared library support. Go for broke. No, good. We're done. Thank you.